Hopefully everybody did a good job dealing with our probabilities of OR problems when the sets are disjoint. So when we're talking about sets that are not disjoint, so from a Venn diagram perspective, it's going to look like the picture we have here, where there's some stuff that's just in A, there's some stuff that's just in B, but then this dark purple stuff is the things that are in A and B at the same time. And so if you remember anything about set theory, this is what's called the intersection. So it looks like A intersect B, like that. So let's look at a little example here. So I've got a picture drawn where I've highlighted some red cards, or all the red diamonds, and all the jacks. So if I was trying to figure out what's the probability, oops, of getting a diamond or a jack, if I went into it blindly, just kind of like what we did last time, then I would notice I'm going to get 13 out of 52. And if I look, I've got 4 jacks. And so I'd add this up and get 17 out of 52. But hopefully at this point, some people are looking and going, oh, whoa, wait a second. So if we notice, this jack of diamonds occurs in both the row and the column. So by doing what I did above, I've actually double counted it, because I counted the jack of diamond in the 13, I counted the jack of diamonds in the 4. So this 17 over 52 is a bigger answer than what we should have. So what we have to do is we have to get rid of one of these jacks of diamonds that we counted above. So what we want to do is subtract out that overlap, the thing that they have in common. And since for this one, we just have that single card, so we're going to subtract 1 out of 52. And so in reality, the probability of getting a diamond or a jack is actually going to be 16 out of 52. So that's what we're going to deal with if our sets have overlap. So we're going to start just like we would before, just kind of assume there is no overlap, and then check, see if there is overlap, and if there is, subtract out how many things that are in common to both sets A and B. So to formalize it, if we look at our general addition rule, so our probability of A or B, again, is going to start off the same way, probability of A plus the probability of B. And then what we need to do is minus anything that lives in A intersect B, anything that's in that common part between them. And so the nice thing is this rule applies even if the sets are disjoint, because if the sets are disjoint, then there wouldn't be anything in there, so we'd subtract 0 away. So this rule actually does work even in the disjoint case as well. And so on the bottom, again, I've got kind of a set theory way to think about what this would look like. So an OR problem, again, is our union. So A union B equals the number of elements in A plus the number of elements in B minus the number of elements in the intersection subtracted out. All right, so let's take a look now at somewhere we've got some possible overlap. So for example 3, we're drawing again a card from the 52 card deck. What's the probability that we get a king or a spade? So in this case, we're looking for the probability of a king or a spade. So again, start off just like we would before, pretend we don't know whether there's overlap or not. So we're going to get the probability of the king plus the probability of spades. And so we know there's 4 kings. So our probability of a king is going to be 4 out of 52. Our probability of spades is going to be 13 out of 52. And so when I add them up, I get 17 out of 52. So now we want to ask the question, is it possible that there's overlap? So is there, for example, a king of spades? And so it turns out, yes, there is, and there's just one card that is overlap, so just the king of spades is the only overlap. So in this case, we just have to subtract 1. And so that's going to give us our 16 out of 52 for this one. All right. So let's look at the next one. So what's the probability that we get a queen or a face card? So the probability of a queen or a face card. So again, let's start off not worrying whether there's overlap or not. So our probability of a queen is going to be 4 out of 52. Probability of face card, 12 out of 52. That gives us 16 out of 52. But now we want to look and see if there's any overlap between these sets. And since all the queens are actually face cards also, then we can subtract out all 4 queens. So in this case, we want to subtract all 4 queens. And so we're going to end up with just 12 over 52. All right. So another way that you can see data represented is in like a little chart we have here. And this is kind of a nice way to, if you can, represent the data, because we'll be able to see exactly what the overlap looks like. And I'll show you by kind of highlighting the rows and columns that we're going to be working with. All right, so for this one, we've got some information about whether a student is an education major or a math major, and whether they're right-handed or left-handed. And we surveyed 130 students to find this out. So we're looking to see if one person is randomly selected from the group, what's the probability the student is an education major or left-handed. So what we're interested in is we want to know whether they're an education major. So we're looking along this row. So let me write this out. So ed or left. And so we can see this is going to be the probability of education plus the probability of left-handed. And so it looks like we have 71 education majors total. So we're going to get 71 out of 130 as the possibility of getting an education major. Now the probability of finding someone that's left-handed is going to be this column. So it looks like there's 25 left-handed students total. Oops. Oops, I'll keep doing the same thing. So we're going to get 25 out of 130. So we add this up, we're getting 96 out of 130. But now we want to look and see if there's any overlap. And so if you notice on the little chart that I drew, it's subtle to see, but this little section here is a little bit darker because the pink is drawn twice in that case, because there are 13 students that are both education majors and left-handed. So we want to subtract, there's 13 from our list, and that takes us down to 83 out of 130. All right, so let's look at the next one here. So I'm going to erase this so we can do the same thing above. So what's the probability of selecting a math major or a right-handed student? So we're looking at math or right-handed. So again, just start off like we don't know or care whether there's overlap just yet. So the probability of a math major is going to be this row. And so we can see we have 59 math majors total out of 130. And then our right-handed students are going to be these 47, or no, 105, sorry, I was looking at the middle. And so with this, if we add it up, we get, what, 164 over 130. And so this is nice too, because remember, what's one of the big rules we have about probabilities? They always have to be less than 1. Like they always have to be less than 1. So the fact that our top number is bigger than our bottom number is telling us right away, whoa, something's wrong. There definitely has to be overlap here, because I can't have more on the top than I have on the bottom. So with this one, let's go back up, and we can see the double highlighted part is going to be the 47. So we want to subtract 47 from 130, and then that gives us, I'm trying not to mess this up, 117 over 130. So the probability of getting a male or a right-handed student would be 117 out of 130. All right, so very good. So try practice 3, practice 4, and then on the next video we'll come back and we'll talk about our complements or not problems. So good luck.